So backing up a little bit in the context of what we've been doing with matrices, if we think about coordinate systems that we've thought of all along, this is the traditional way of creating a coordinate system. We describe a point in here by saying how far over we went one direction and then maybe how far up we went. So maybe this is the point 4, 3. And we describe that in the context of how far over left or right, how far up or down. Right? That's what a coordinate system does. If we think of this in the context of vectors, we have a vector 1, 0 that points that direction, and we have a vector 0, 1 that points that direction. And so when we think about the point 4, 3, we're really saying how many times did we apply vector 1, 0, and how many times did we apply the other vector 0, 1. And so we're thinking again the position in terms of some arbitrary origin, but from that origin everything else follows. And so from here we say how far over, how far up did we go. So what we really have with coordinates is we really have a description of that operation in terms of these pieces. So let's think about the point 4, 3. Well, the point 4, 3, thinking in terms of vectors, we will think of as the vector 4, 3 with the tail at the origin, the head at the point 4, 3. Right? So that's our typical way that we've been going back and forth between the point and the vector. And as far as coordinates go, we say how many times did we need to apply the 1, 0 vector, a movement by 1 in that direction, and how many times did we need to apply motion upward in order to get this point. So when we think about coordinates, what we're really thinking about is creating, this is a times here as well, thinking of creating a way of combining motion to the right and motion up. Now, if we were going down, then what would happen? These A or B values, if we were going down, A would be negative. If we were going to the left, B would be negative. But what are we thinking of? We're saying how many times do we apply motion to the right, and then how many times do we apply, in this case, motion upward? And so what happens? If we look at this, A times 1, 0 plus B times 0, 1 is the vector A0 plus the vector 0B. And if we're trying to get to the point 4, 3, that needs to be 4, 3. So adding this together into one vector, we have the vector AB has to be equal to 4, 3. Well, if AB is equal to the vector 4, 3, what does A have to be? A has to be 4, B has to be 3. And so when we talk about the coordinates of a point in terms of a vector, what we're really thinking of is how many times, how much of this is in our answer and how much of this is in our answer. What if the point had been, say, 1.5, 0? 1.5, 0, well, we would have needed 1.5 of these. Go to the right one, go to the right another half, and then none of those. Right? And so the coordinates of the point in this case are really just these coefficients. We don't tend to think of them that way originally, but that's what we have said we're doing. How far to the right are you moving or left? And then how far up or down are you moving? And so this idea of a number times a vector plus another number times another vector. This is called a linear combination of vectors. A linear combination because if you think about the 1, 0, that kind of represents the x, and the 0, 1 represents the y. And what do we have? We have ax plus by. And what is that equal to? This is equal to some target, some particular point that we want to reach. All right, so a linear combination of vectors builds a new vector, or maybe builds an existing vector, but it builds a vector. And so in a linear combination, we have a and b are just numbers, and then we have the vectors. And so what happens if we wanted to build the vector 3, 5? What would we do? A is 3 and b is 5, right? So this is, it seems, again, with these two particular vectors, the coordinates they correspond to the point itself. Well, what happens if we have maybe a different set of vectors? Well, we have a different set of vectors, and maybe things behave a little bit differently. But before we get there, let's look at these two vectors. And think of it as a set of vectors. If we don't have to worry too much about the details there, but we have this set of vectors. Let's say we call it S. Right, just a set of vectors. In this case, these two vectors. The span of S is another set. The span of S The span of S is the set of vectors that are a linear combination of vectors in S. In other words, these are all the vectors that you can construct from those pieces. And you construct a vector from these pieces by making linear combinations of them. All right, so what do we have? We said that if you build a linear combination of these two, you get things that look like this. What looks like that? What is this? What vectors can we create? Any two-dimensional vector that we want, right? We pick A to be the first component and B to be the second component, and we can create any two-dimensional vector that we want. And so what is the span of S for this set S? The span of S is all of 2D space. Right? Any particular, if you want to create a two-dimensional space, again, this is based on having a particular origin. You have that particular origin, you have those two vectors, and you can construct anything that you like. Now, what if we only had one of these? What if we only had this vector? We want the span of that one. So what would we be able to construct here? Anything with an x, right? What has an x? It has an x and a 0 for the y. So what kind of thing has an x with any x value with a 0 for the y? We can construct the x-axis, right? So with this one vector, we can only construct the x-axis. Right? The one vector was this one. So the span is limited. It's not all of two-dimensional space. It's just a single line. these two together, and we can construct all of two-dimensional space with this linear combination. All right? So what happens is we will be looking at scenarios that this coordinate system doesn't make sense for us. If you think about, you're looking at me right now, and if I say, let's all move to my left. My left is this way. That's not your left. But you could all move to my left, right? Making them move in that direction. But for you, depending on how you're sitting, right? If you're facing me directly, then moving to my left is moving to your right. So there's a different coordinate system, a different thought process in place. If you're sitting kind of angled toward me, then moving to my left, if you're over here angled toward me, moving to my left is moving kind of back and toward your right. If you're sitting on this side angled toward me, then moving to my left is moving kind of towards your right, but it's in a forward, facing forward. So it depends on where you're facing, what my left is. And often we have that situation of different objects having different coordinate systems. And if I say, let's all move to my left, we're people, we can think about it, we can do that. But what if we're trying to tell an object in a program how to move when it needs to move to my left? And so we need to be able to transition between different coordinate systems to describe things in different ways. Sometimes we're transitioning from an object to what our author calls upright space. So from the object axes, say we have an airplane. So if there's an airplane, this airplane has an X, a Y, a Z that correspond to the plane. And then there's an upright space, X, Y, Z, and that plane, depending on how it is in that system, is its X, Y, Z values don't change, but the global do, or they're fixed. Right? So it's consistent here. Let's put it this way: it's consistent inside the plane. Inside the plane, if you reach up, you reach like that. But where is up? Up might be like this. If you're in a dive and you reach up to touch the top of the plane, you're going to reach this direction, right? If you're flying level, reaching up. So up is different depending on where the plane is. If we say actually reach up and do something, or reach to your left. Where's your left? Well, your left is, you know where your left is. Even if you're upside down, you still know where your left is. But your left may no longer be my left. And so we need to be able to transition between coordinate systems, and that's what this idea that we're talking about right here does. If we look at this vector by itself does not span all of 2 dimensions, but the two of these together do span all of 2-dimensional space. And so we say that this original set S there's a technical aspect we'll talk about in a minute, but we say that S is a basis for 2D space. What does a basis mean in this case? A basis means that you can build 2-dimensional space from these pieces. All right? So you can build all of 2-dimensional space from these pieces. There's a slightly more technical aspect we'll talk about in just a couple of minutes.
All right, I'm curious now. So you have that zipper pocket.
Mm-hmm.
Do you have the side pocket as well?
Yeah.
Like, does that, okay.
Yeah.
I wish it was like a fake pocket.
It's real. So this idea of a basis is having the right number of pieces to be able to construct everything that you want to construct, right? So the span is, in this case, two-dimensional space, and if you take one of these away, you don't have enough to span two-dimensional space. And so you have just the right number of pieces to be able to describe everything. Well, if we only had these two as basis elements, then this is a lot of work for no reason. But what if we instead decided that we liked a different set of vectors? What if instead we liked these vectors? Can we still describe everything in 2 dimensions with these pieces?
You can describe all the evens of X.
Well, so let's see what happens. Let's see what kinds of things we can describe.
Actually, yeah, you can.
So what do you build with this? What does this look like? 2A and B. So what if we wanted to describe, say, that point again that we had mentioned, 3, 5? So to describe the point 3, 5, we need to be able to build the vector 3, 5. Can we build that from these two?
You use fractions from.
Yeah, so what does A have to be? Well, so 2A would have to be 3, right? Because that's what we construct here. So A is 3 over 2, so 1.5. And B is 5. Okay, so what have we done with this? We can still build that thing. Can we build anything? Is there some? It was still 2-dimension, right? Because we're still talking about 2D space. We can't build anything 3-dimensional with this. We're only talking about 2D space. Can you build everything in 2D space with this?
I believe so.
Yeah, what do? We just make the A part be half of whatever we're looking for, and then the B part, we leave it alone. So what does this do? This makes the Y scale the same, but what does it do to the X scale? The X scale, this corresponds to 1 unit, which is twice as far as it used to be. So we've changed the X scale. What is the point 2, 0 in this new coordinate system, right? So what we would say in this case is the point 3, 5 in the old coordinate system matches with the point 3/2 5 in, I don't know, put some squiggle on there, right? 3/2 5 in the new coordinate system. So in the new coordinate system, what was the point 3, 5 is still the same location in space. It just has a different name now.
So this is basically how we treat going to your left.
Yeah, so we can treat, how do we treat going to my left? We have to figure out what 1 unit to my left corresponds to in your system. Right? So in your system, that means go this far in this direction, right? Whichever that happens to be. So what happens? The point 3, 5 in the old system is still the same geometric location, but that was just a name we gave it. But now we're saying, oh, we're not describing things in terms of going this way 1 unit. We're describing things in going this way 2 units in the old way of measuring. But what does the point then 2, 0 correspond to in this new system? In this new system, if we're trying to build 2, 0, yeah, then A is 1 and B is 0. And so the vector 2, 0, or the point 2, 0, in the old system corresponds to the new point 1, 0. Right? Because we've changed the scale. Do you ever change scale when you're drawing something? Do you ever have different scales when you draw a graph, let's say, in a maths course? We often have different scales. We might have time down here and money up here. Well, the scales are definitely not the same when we're talking about time and money, right? Because they measure different things. So a unit here corresponds to 1 unit of time. What might 1 unit of time be? 1 unit of time might be decades. 1 decade, the next decade. It might be actual years. It might be months. It might be different things. We might change the scale depending on what we're doing. This might be in actual dollars. It might be in hundreds of dollars, thousands of dollars, millions of dollars, depending on what we're measuring. And so the scale, we change the scale quite often. We tend to not change the scale by using something that is twice as long, but I mean, we tend to not change a basis or coordinate systems by using things that are twice as long, but sometimes we do. And so what does this particular situation do? This changes the x scale. And so what we thought of before as the 0.35 in the old system, we would have to think about as the 0.3 5 in the new system, but we could make it work. Other things, we change the scale, so lengths are different, and there are some other issues. So often, instead, we will change it in a way that the new coordinate system is based on things that have length 1, but not always. So let's look at a different situation. Instead of this, what if this is the regular xy? What if I wanted a vector in that direction? So a vector in that direction, what is that? What is the equation or the standard equation for that line? So like we did in slope-intercept form, it would be y equals x, right? So that could correspond to this vector 1, 1. Y and x are the same. What about this line? Right? Y equals negative x would be the slope-intercept form for that. And so what could we do? Maybe this way we have 1, negative 1. So y is the opposite of x. Or actually that point right there, that's the wrong one. Let's do it that way, negative 1. Right, for the one that we drew. The other one, 1, negative 1 would be down here. Well, if this was our original coordinate system, what would this possibly do? What does it look like it does? It takes things and rotates it, but then it also messes up the lengths a little bit, right? Because how long is this vector? This vector's length is 1. This vector's length is 1. So these are unit vectors. How long are these vectors? The length would be square root of 2. Right, in the old system, right? In this system, these have length square root of 2, right? So again, typically we would make these be unit vectors in this situation, but they don't have to be unit vectors. So what if we wanted to describe our 0.35, or actually let's describe the point 1, 0. So 1, 0 is here. All right, so let's describe the point 1, 0 in this new coordinate system. So what do we have? We have A times 1, 1 plus B times negative 1, 1. And we want that to be the point 1, 0. So again, we want to create the point, so we have to create that vector to describe that. All right, are there choices? Can we put things in here for A and B that will give us the point 1, 0. So let's look at what happens with this. What do we have here? We have AA. here we have negative BB, and we need that to equal 1, 0. All right, so combining this, the vector on the left, the linear combination that we have created, looks like this. And then on the right, we have 1, 0. So what does this mean? This means that A minus B has to equal 1, and A plus B has to equal 0. And what does this look like? This is a system of equations. Our matrix stuff that we talked about before tells us how to solve this. Or again, it's a 2 by 2, so we can solve it without going to a matrix. But what happens in this linear combination idea to see what the coordinates happen to be sometimes means we have to solve a system of equations. All right, so let's solve this system of equations. How would you go about solving this system of equations?
Get one variable.
All right, we could eliminate one of the variables, but in this case, it's already set up for us, right? Negative b and b. So if we just add these two together, what happens? We get 2a equals 1. So a is 1/2. And then if a is 1/2, what is b? B will be negative 1/2. All right, so what does that mean? That means to get to the point 1, 0, we have to go half of the way on this vector. Oh, made that too dark. Have to go half of the way on that vector. And then do what? Then go half of this vector in that direction, right? So we go this direction, and then half of the opposite direction, right? So we have to go half of that one in that way. Does that make sense? So if this was the new x and y, then the old point would now be thought of like that. All right, again, because these vectors aren't unit vectors, the lengths have been distorted and changed, but the idea is that we have described that old point in the new way. Can we describe every point using these two? If we have, okay, a new S, is span of S all of two-dimensional space? Well, again, let's think about what happens when you create a linear combination here. We had this, and the question is, can we create any other vector that we like? So can we create any vector CD that we want? Well, let's see what would happen. So a minus b would have to be c, and a plus b would have to be d. Can we always get a choice for a and b? Well, if we solve this, we have 2a is equal to c plus d. So a needs to be c plus d over 2. And then what can we do? We can put that back in. We know c and d, they're actual numbers. So we can always put that back in and find out what the b is. Right? There's no a, there's only b equals something with c's and d's, and c and d are actual numbers. So what does this mean? This means, yes, we can build everything with those two pieces? What if you take one of them away? Can we build everything with just one of the pieces? What if we had just 1, 1? What can we build with just 1, 1? Right? With just 1, 1 multiplying by a number, we can just build that one line. With just negative 1, 1, we can just build the other line. But with both of them together, what can we build? All of two-dimensional space. All right?
So if this current coordinate system that we're using, if that can find all 2D space, is there a coordinate system that we can't use?
Well, good question. Let's see. Let's just try something. So is everyone okay with the fact that we can build everything in this new coordinate system? It changes our distances and, of course, changes the actual coordinates because, like, what used to be 1, 0 is now 1/2, negative 1/2. We've kind of tilted our head and we messed up the distances. Again, normally we would use something that doesn't mess with distance, but in this situation, I mean, sometimes we do mess with the distances. All right, so let's look at a new space here. Let's say we have 1, 2, and 2, 4. All right, let's see what we can construct. If we can figure out what span of T is. What's the span of T? All right, so what are we looking at? We want to see what we can what this looks like. So what do we have here? We have A and 2A plus 2B and 4B. So we have the kinds of things we can construct look like this. All right? So same situation. Okay, so let's see. What do you want to give me a number for the first 5? And give me a number for the second coordinate. 8? Yeah. All right. So we want to construct 5, 8 from this. So we need, this is what we need, right? We need the things that we can construct to be that. All right, so what does that mean equation-wise? It means that A plus 2B has to be 5, and 2A plus 4B has to be 8. All right, let's use the elimination procedure. We need to multiply this top equation by what? A negative 2. So if we multiply that by negative 2, we have negative 2A minus 4B equals negative 10. And then we have 2A plus 4B equals 8. And what happens on the left-hand side? We get 0. And on the right-hand side, we get negative 2. What does that mean? That means that we cannot build 5, 8. Because there's no choice of A and B that we could put in here that would give us 5, 8 as the output. So what does that mean? Span of T, well, we still don't know what it is, but it's not all of 2D space. It's something. There's something that we can build with those two vectors, but it's not everything. So let's see what we can build. What can we build with that? We can only build vectors that look like this. Right? These are the things that we can build. So let's take a look at this. A plus 2B and 2A plus 4B. We can factor that, can't we? Factor a 2? What do we get? A plus 2B. So what do our vectors look like? Our vectors look like some x value and then 2 times that same x value. Well, what is this? This is x is x, and y is equal to 2x. What can we build from those pieces? We can build the line, which I didn't make quite steep enough. We can build the line y equals 2x. Does that make sense? So this time, from these two pieces, we don't build everything, we just build the line y equals 2x. You had a question earlier, I'm sorry.
Is there a way we can tell this right off the bat when seeing it, whether or not it's
Good question, because that was the next direction that we're going to go. All right? So what did we have? We had our set of vectors was 1, 2, and 2, 4. We know that those two now just construct this one line. Notice that if we look at the linear combination structure with these, to see if there's any redundancy in the information, what we can think about is what would the coordinates for the 0 vector be? Right? We want to figure out the coordinates for the 0 vector. And so what should the coordinates for the 0 vector be? In general, the coordinates for the 0 vector should be 0, 0. Right? Because the 0 vector is the origin, and so the origin in the new system should also be 0, 0 in that case. Well, what happens if we put a and b equal to 0? Then we do get 0, 0. But our question is there a different way to get 0, 0? And if there's a different way to get 0, 0, what that means is that there's redundancy in our information. So let's see what happens. If we put this together, we have a plus 2b is equal to 0. And then we have 2a plus 4b is equal to 0. And if we do the subtraction that we just did with multiplying by -2, we end up down here somewhere with 0 equals 0, which means what? In a system of equations, when you get 0 equals 0, what does that mean? If you get 2 equals 0, then you know there's a problem, right? There's no solution. But what if you get 0 equals 0? If you get 0 equals 0, I mean, when is 0 equal to 0? It's always equal to 0, right? And so what this means is that these equations have redundant information. This means that there's infinitely many solutions to the system. So let's think about, for instance, what happens if I make a equal to 1 right here. What could I make b equal to? Might be easier to do it the other way. Let's make b equal to 1. What could I make a equal to? Zeros. If I make a equal to -2, then we get 0, right? So what this says is that the coordinates for 0, 0 are ambiguous. You don't have to put 0, 0 in here. You could put -2, 1. Or you could put 1, -1/2. In other words, these two have repeated information. There's redundancy. 1, 2 times 2 is equal to 2, 4. So what you can build from the two of them, you could build from just one of them. Does that make sense? Anything that you could build with both of them, you could build with just one. The second one doesn't add anything extra to the description. So it doesn't allow us to create an actual coordinate system for like all of two-dimensional space. Right? So here's what we think about. So we're given a set of vectors. How many ever vectors we have? V1, V2, how many ever there are, right? Vk. We have k vectors. And they're all two-dimensional or three-dimensional, or they're all the same dimension in the individual vectors. But there are k of them. The set S is linearly independent if there's no redundancy, which means if the only solution to this equation is that all of the values, all of the coordinates are 0. What this means is there's no way to write one of these in terms of the others. If you can get some of these numbers not being 0, that means that you can write one of them in terms of some of the others, as a linear combination of some of the others. And if you can write one of them as a linear combination of some of the others, what does that mean? That means that you didn't need that one. That means that there's redundancy, and so you don't have this independence, and so you don't have the right information in order to create a coordinate system. Okay, so what happens? That means that this set, you can't write one of these in terms of the others. If you want to get 0 out of this, you have to make both coefficients equal to 0. So this is a linearly independent set. Whereas this set is not independent, and we say in that case that it's linearly dependent. So for a coordinate system, we need independence. We need to not have redundant information. Because if we have redundant information, we can't properly describe locations anymore with those two pieces. There's more than one way to describe them, to describe certain points. And so having more than one way to describe certain points messes up the whole idea of a coordinate system. But if you have independence, then you can create a coordinate system. So the slightly more formal definition for the basis is if S is the set of vectors if it's linearly independent and span of S is the whole space that we care about, two-dimensional, three-dimensional, or whatever, then S is a basis for the space. Okay, so what's the idea? That we're able to transition from a space with a coordinate system to the same space with a different coordinate system. So we change the basis. And there's a lot more details and a lot more information and so on. But everything we've been doing when we've been rotating things and then thinking from that new perspective, if we had an object and we rotated it, then we still want its right to be its right, not the original object's right. So it's rotated and right goes with it. So the directions change. Things change appropriately. So if you have a basis for a space, then you have a coordinate system that you can deal with. And so when we look at this is a basis for two-dimensional space. This is called the standard basis. It's the normal way we think about it. The set 1, 2, 2, 4 is not a basis for two-dimensional space. You can't build everything in 2 dimensions. So how many vectors do you think you need to construct all of two-dimensional space? So how many vectors have to be in a basis? There have to be 2, right? There has to be something that gives whatever left and right means, and there has to be something that gives whatever up and down means, and those 2 can't be multiples of one another because left, right, up, and down then get messed up. So not just any 2 will work, but a lot will work. In a basis for two-dimensional space, usually, again, we're looking for things that are perpendicular to each other. But sometimes there are scenarios where we have skew kind of things, where you have a weird coordinate system like that, and that still works. That's still okay. And there are reasons for it sometimes, but usually we want perpendicular, and usually we want these to have length 1. So what we talk about in that case, we've seen this word before, we usually want an orthonormal basis. It's usually what we want, right? Ortho means what? That's the perpendicular part. Normal is, in that part, means that the length of each vector is length 1. They're unit vectors. And then a basis means that we have enough pieces to build the whole space. So what about 3-dimensional? What do you think in 3-dimensional space that we need? How many vectors? We need 3, right? We need left, right, up, down, forward, and back. We need something to be able to describe those different directions. Again, forward and back might not be perpendicular to the others, or none of them have to be perpendicular. But again, what do we usually do? We usually like to keep them perpendicular and keep those units as unit vectors, or keep those vectors in each direction as a unit vector. So the idea of what we've been doing with matrix multiplication really corresponds to changing coordinates between one position or one thing and something else. And often what we want to do will be change coordinates between some standard thing that corresponds to what our author calls upright space and our object axes. So on the object we'll have an XYZ axis. Upright space has an XYZ axis, and we want to be able to transition from one to the other. These are usually, they can be either for location, like we're talking about here, or it can be just strictly as vectors for orientation purposes. And so we will talk about the orientation aspect in a separate in a separate video, but in just a minute when we start.